Okay, so we went again through the calculation from last time to show that the charges that generate supertranslation and superrotations commute with the S matrix. We used the fact that we can split into soft into hard. Then we figured out the action of the hard charges on the in and out states. We wrote down the soft operators, which are essentially this U integral of the news. We used the fact that integrals over U with powers of U and derivatives of U map to the zero frequency limit with certain powers and derivatives with respect to the energy. And then we found an expression, which is the left-hand side, where we can use the soft theorem to recast the insertion of a soft graviton of negative helicity in the out state by the amplitude without the soft particle, but multiplied by this soft factor. And then we plug this back into this full expression, which also had this integral over the sphere. Now, in order to show that this is actually the right-hand side, we integrated by parts to move the covariant derivatives around, hitting these factors. We wrote these factors in terms of the angle coordinates and energies, and then got a bunch of delta functions so that we can integrate this expression. And then lo and behold, the left-hand side really is equal to the right-hand side. So what this amounts to what this boils down to is the fact that the soft graviton theorem implies that BMS group, or extended or generalized BMS, because we haven't even said what F and Y are, is a symmetry of the S matrix. Now, conversely, we can also ask whether the water identity for these symmetries does actually imply the soft graviton theorem. And for that, we choose particular expressions for F and for Y. So for example, for F, we'd have to choose something like a singular function that looks like this, whose second z derivatives gives a delta function. And then the vector field yz will have to be this non-meromorphic function, which when it's hit by 3 z derivatives, it's also a delta function. And so then we can invert the statement of going between the asymptotic symmetries and the S matrix. Last time I got a question of what of this holds when we have massive particles, which come in from past time lag infinity and go out to future time lag infinity. And here I put 2 references by Campilli and Lada, who investigated this soft theorem asymptotic symmetry connection. And this is essentially given by these 2 papers here. Okay, so now for this lecture, what we want to show is we want to recast this statement as a water identity. Then we want to see that this water identity actually looks like a water identity in a 2-dimensional CFD. And then we're going to ask ourselves, how do we actually get to this 2-dimensional CFD? Okay. But before I'm going to do this, let me ask if there are any questions on what I explained or reviewed here from last lecture. Okay? Good. So then let me first start by deriving a water identity for what's going to be a Kac-Moody current. Okay. Is there a question?
No.
Okay. Okay.
Shut off your microphone.
Maybe not, yes. Okay, so here, we're going to first look at the leading soft graviton factor. And I'm going to rewrite this in the following form. So if you remember, this is just an expression in the momentum and the polarization vectors, and when we plug in a parameterization for the momentum and polarization vectors, we can write this in terms of the energy and the angle coordinates z and z bar. Okay, so now let's look again at this matrix element that involves the news. And let me write for shorthand this normal ordering, which just says that the news written in terms of the u integral acts on the out state, and the news written in terms of the v integral acts on the in state. And so when I plug this in, let me just write 2 lines what this amounts to. So there was a polarization vector, which became this 1 over z bar squared piece. And then I have this soft vector. Whoops. And now, so this is just a statement of the soft theorem without the integral over the angles. And now I can rewrite this. I can plug in the soft factor. And then this expression becomes okay. So now I want to introduce a quantity that I will call curly P.
Sorry, Andrea, I think I missed. I was doing something else. So this S0 is the soft factor that you introduced in your first lecture, right?
Yes.
Which was written in terms of the momentum.
Yes, I can rewrite it if you want.
So did you explain it, or
yeah,
okay.
We had this.
Sorry, then never mind.
Yeah, so we had this expression. Let me see if I have this expression at hand. So this soft factor was also given by the momenta P dotted into the polarization vector of the soft graviton, and then divided by the momenta dotted into Q. And remind you, normally it's written with, so the soft graviton was again parameterized by energy and some null vector. And then I had the hard momenta, P mu, which were parameterized. Let me put a hat here. Zj, Z bar j. So I gave you some expression for this, and then told you if you plug them in here, there's also an epsilon. I don't know if it's useful to write it down. It's something like 1 over square root 2, and then let's see.
I think it's okay.
One moment. Oh, maybe not. It's just some z's and z bars, but I don't want to write down the z instead of the z bar in that place. It will be in the, or it is already in the lecture notes, but I cannot find it. It's just some expression. It has like a z bar 1i minus z bar or something. If you plug this into the soft factor, then, and I've written this in terms of Q because I pulled out the extra power of omega in front of the soft theorem. So maybe the soft theorem was just at the n+1 amplitude where you have this soft particle. When you take the zero frequency limit, becomes a pole in omega, and the soft factor plus an order 1 piece times the other soft factor times the amplitude without the soft particle. So that was just a statement. And here, this is just a soft factor with this parameterization, which we'll discuss much more today. And then plugged into gives this expression. Then we plug this into this matrix elements, which gives us the soft insertion. And now I want to recast this matrix element as a word identity. So let me introduce this quantity P, which will be given essentially by a derivative of the soft operator n0. So this is just the definition at this point. Now I plug this in. And again, the one that's written in terms of a u integral will act on the out, and the other one that's written in terms of the v integral act on the in state. And then this expression reduces to something very nice. So essentially now we have an extra z derivative hitting this whole expression on the right. So this will kill this term up there. And then if we reshuffle the things, the expressions here, it will just become this simple looking quantity. So it's just given by, let me write it a bit more clearly. It's just given by this expression. Then there's another term, but this other term is 0 by momentum conservation. Okay, so what we have here looks very much like the water density for a Kac-Moody current.
Sorry, Andrea, just to understand, is there some simple physical explanation as to why you get poles whenever the z bar of the soft graviton is aligning with the z bars of the massive particle? Sorry, the hard particles.
Well, we have collinear limits, which is exactly that. That you have, so you have the momentum of one particle going aligning with the momentum of another particle, and if you write this in this z and z bar coordinates and the zj and z bar j coordinates, which we'll discuss much more in detail in a moment. If you aligning momentum amounts to setting the z and z j's equal, so then you get these.
But it seems to be asymmetric between z and z bar.
What do you mean?
The numerator is z's and the denominator is z bars. Is there a simple physical explanation for why that structure appears?
Well, okay, first of all, to say that the leading soft graviton is a bit funny just precisely because of that. And for example, later when we discuss OPEs, we will also have terms like that, and not just one over one of the holomorphic or anti-holomorphic coordinates. So that's a funniness of the OP, and it has also to do with the kind of conformal weights that we'll later find these objects have. Maybe let me write down also the water density for the stress tensor, and then we will not have this, but this is a feature of the fact that supertranslations are a bit funny in that respect. Okay, so yes?
Clarification. You were saying that this collinear limit has this power of bar minus c bar j in the denominator. It's also a little bit like, I mean, should I think of this like a light cone limit where, so you hold z fixed and take z bar of, two particles or something to coincide? Is that, what's the relation between the collinear limit you're talking about and the light cone limit where like one operator approaches the light cone with another? Is this at all similar or not?
There's probably something to say here, but I'm not sure we'll talk about OPEs, celestial OPEs, probably in the next lecture. So maybe we can discuss afterwards, and you'll tell me what exactly you have in mind, and then we can see if there's something that I can say in the next lecture.
But just at a very simpler level, are you saying that it's known that in the collinear limit divergences look like that? So
yeah,
that's just some basic fact about collinear limit?
We'll derive it in.
So isn't it just kinematics? Like if you gave me the exercise to compute when speed was q.
Here I haven't said anything about OPEs or whatever. I know. Yeah. So
I'm just trying to understand
exactly.
how kinematics implies those factors, because I'm not used to this coordinate.
Yeah, so actually the kinematics will be about embedding the complex plane into the light cone of Minkowski space. So it's, there is some relation to what you're saying. Well, the fact that this turns out like this comes from plugging in what these expressions are. So, yeah. Okay. So now, okay, this looks like a Kac-Moody current water density, but we also have this extra power of energy in here. And usually when we write correlators that involve such a current, so I'm going to write down a bunch of operators and put some labels which will, which refer to in and out states here. So they would have expressions without this factor of omega, which is kind of a hint already that the this object, which is called the super translation current, will do something funny in a basis where we can write these S-matrix elements as correlation functions of operators. And what this will do, I will denote this operator OJ by a prime. So that's to say that this extra power of omega here will do something to the operator with the same label in the sum. Okay, so much for super translations and what I did that is implied by the leading soft graviton theorem.
Sorry, just can all the people online please shut down their microphone? Thanks.
It's a USD.
Who else?
I just did.
Okay, so this is the main result here of, maybe let me give the references here. So that was Strominger, and this one is Hale-Isov, Mitra, and Strominger. All right, so now onto the stress tensor. Okay, so again, we rewrite this S-matrix element. Let me just write it down again for you after we parameterize the momenta in a way that we'll talk about more later. So we have an expression So this is using the soft factor when it acts on the in and out states, because in the subleading soft graviton case, it's an operator, as you can see from here.
The noise is back. I don't know if anybody did anything. It just started to make this horrible noise again. And now it stopped completely, the sound.
Hello?
The noise is back. I don't know if anybody did anything, but the noise just came back in full.
I'm not sure what I should do. What do you want me to do?
I don't know, Ricardo. Is anything what you did? I mean, it just started like half a minute ago. Usually stuff doesn't start like that, so.
is the following. Okay, let me already replace this by something that I want to introduce, which is hj plus, again, the Christoffel here. Okay. So this is the result that you get, where I have now introduced hj. And hj, if we are talking about scalars, will be just given by -1/2 omega j d omega k. So this is just the operator that I wrote before. So I did nothing. I just called it h. Okay? But now if we stare at this, then we recognize that this is the water density of a stress tensor. Provided that this actually is a number. So what we have to do if we really want this to look like the water density of a total stress tensor, so that's the statement that we have the stress tensor inserted into a correlation function with operators O1 to On, and then maybe I just copy it again. It's just the same as what is written above. So if you can't read it, it's just the same as the line above. And now we have this correlation function here. Okay. So if we want this to be the water density for a stress tensor in a correlation function with operators O, then we should change the basis of scattering states where this derivative operator hj, this guy here, actually becomes a number. So we want to find a new basis of scattering states that does not use energy momentum eigenstates, but one where this operator, the action of this operator, is diagonalized and just gives us a number. So that will be the goal for today. I think the way it went is that you notice, but then later when we will talk about the conformal multiplet structure, this will arise naturally as a current that's holomorphic, and so something that we want to look at. So at this point, so this derivative, do I have an expression somewhere here? Yeah, so this. So this n z bar 0 is this element, right? It's omega, and then there is an operator that inserts it. And when I go from n to p, then there will be an extra derivative that hits this creation. It's a creation operator in the outset, right? So what it will boil down to, once we have to introduce celestial CFT, is that this operator will be the descendant of a soft graviton operator. So this will create a soft graviton, and this will be the descendant of that. Yes. Yes. Mm-hmm. Yeah. So here, well, here we have. So in the CFT, you will not have omega. You will have operators labeled by delta and j, and the locations where they're inserted, right? So the comment, which at this point is a bit cryptic because it's not clear yet what will happen, but this extra power of omega, after we transform our 4-dimensional statements into 2-dimensional statements will amount to doing something to the labels of that operator. So we will arrive at a map where we trade energies for conformal dimensions. And then well, here you can sort of read off that the OPE of P with another operator of energy omega has this power of energy. And then when we go to the conformal basis, where you don't have an operator that's labeled by the energy, but an operator that's labeled by delta, the OPE with P will shift the conformal dimension of this operator, and that is what I denoted by prime, because I haven't introduced yet how delta and J and everything appears.
But sorry, just at the level of this boxed equation, there's no problem with omega. Could you say that the omegas are the charges, and this looks exactly...
And if this is a U1 current, then this is precisely what happens. This is a well, then you don't have the derivative, but then you have a current, and then this is the charge.
Yeah, because this omega is related to translations in U, whereas you're looking at the structure on the sphere, so a priori, you can just from this equation, you may naively think that you could disentangle them and just consider omega as a charge. Am I understanding correctly that the reason that you have to go to the different bases is because you have these operators Hj on the next slide,
yes.
which are really making things complicated.
That's the reason. I thought about introducing this before, but then this is more complicated than this, so that's how it went. But here you see that if you want this to be a stress tensor, you have to go to a basis where this is a number and not this operator. And then when you do that, what will happen is that when you translate this statement into this new basis, is that this omega will do something to the jth operator. And we're going to talk about this.
The new basis, the action of the Kac-Moody current is no longer diagonal.
Yeah, translation symmetry is obscured in this new basis that we introduce, which on the other hand makes conformal properties manifest.
So you either have a basis in which the Kac-Moody is diagonal, or you have a basis in which the stress tensor is diagonal.
Yeah, if you wish.
Something like that.
Yeah. And this is related to the fact that in one basis really has manifest translation symmetry in the amplitudes and everything, and the other basis has manifest conformal symmetry. And the other one is obscured, respectively.
I see, nice. And sorry, can you remind me what this gamma was? Gamma
This gamma here?
No, the gamma. That enters in your
This is the Christoffel on the two-sphere. So here we're looking at the water density on curved space, and it's just given by minus 2 z bar over 1 plus z bar. And then if you have not just scalars, then there's extra terms with spin, and then this operator gets an extra plus sj here. Okay? But that would have been too much to write. So now we want to talk a bit about motivating what kind of transform you do such that we diagonalize the action of this operator and get go from a basis of energy eigenstates to a basis where the labels are the conformal dimension and the two-dimensional spin. So we are hitting nearly the hour. So I could just go on and talk a bit about the action of Lorenz transformations on the two-sphere, or I reply to Eric's comment from the first lecture about loop corrections to this whole business. I don't know if guys are interested about loop corrections and the interpretation as anomalies or shifting the stress tensor. I can make a few comments about that, but that I think depends on the audience. Eric, since you asked the question.
Yes.
Okay. Okay, good. So just a brief comment on loops. Okay, so when you have infrared divergences in soft exchanges between external lines, they will correct the soft factors. The leading soft factor is not corrected, but the subleading soft factor will be corrected. And so let me write down, first of all, the L loop expansion of these graviton amplitudes. When this denotes the Lth loop factor. And this, so there's power of decoupling, and then in here there will also be powers of decoupling from the n external lines. Now in dimensional regularization, where we have the dimension is 4 minus epsilon, we can relate the one loop graviton amplitude, the diversion part, to the tree level amplitude. And let me just write this down here. So the divergent part of the one loop amplitude is given by this divergent piece, and the tree level, which is the L equals 0 term. And this guy here, well, it's some expression. That I and j running from 1 to n, the momenta, pi and pj, and then we have this logarithm of the renormalization scale mu, and another set of powers of these momenta of the ith and jth particle. Okay, so this piece is a purely IR divergent piece because in pure gravity, the on-shell one loop amplitude is finite and there are no collinear divergences. Then we can look at what happens to the soft graviton theorem where we have an extra particle in the in or the out state that's soft. And here the divergent piece is some different function here, sigma. And then we have the soft factors. I guess I should stick to my notation where the soft factor does no longer have the powers of energy, they're pulled out. And the reason why I'm doing this is precisely because of the fact that when we change bases, we'll do something to the omegas, and I wanted to have them explicitly everywhere so that all my soft factors will just be function of the angles, so that I can then relate them directly to what would be the analog in this new basis. Okay. Okay. And now I can, so this is just the divergent piece, which is universal. Then there's also a finite piece, but this finite piece is not so much is known. So we'll just focus on this infrared divergent piece and what it does to the soft theorem once we include these loop effects. So now let me just write down the full amplitude, finite and divergent part in the omega to 0 limit. That's just given by what we had originally, the soft factors at leading and subleading order. Then there will be this divergent piece here. Oh, and I didn't tell you what that is. I think there should be a prime here. And this prime is given by, well, some expression that's of order omega to the 0. And then, well, I guess I should write it that way. And this is of order omega. So there's potentially a competing effect from this term here. And that is what I'm writing here. Let me just write this out for completeness. And then there could be some finite contribution, but I'll not say anything about that because not much is known. And then there's the amplitude without the soft insertion. Now, if you now compute again the matrix element that we computed essentially here, and then look at the divergent piece, what this tells you, so, well, this here without the finite piece, it will tell you that once you insert this and compute again the matrix element with this stress tensor that we defined, is that there's a shift in the stress tensor, okay, so there's a new stress tensor then, which is the old one that we computed from this tree-level subleadings of graviton theorem, and then it will be shifted. And this shift, you can then express it again in terms of ends and derivatives and so on, and this is rather complicated to compute. So let me just write the results so that you have something to look at. So there's this epsilon here. And then we have some expression. So there's again this integral over the sphere. And then we have a shift that involves the leading soft graviton operator. And okay, so that's this expression, which is a bit non-trivial to arrive at. But that's the interpretation. So you have loop corrections to the subleadings of graviton factor. The subleadings of graviton is one loop exact, and you can write down what the, so this is kind of an anomaly, and you can write down how the stress tensor gets shifted by this effect. And then when you plug in this new operator, the one that's been shifted, then you will get, again, the water density, now for the new stress tensor. And because there are no other, so the origin of this is really IR divergences, this has been interpreted as sort of an IR renormalization of the stress tensor. And let me also give you the reference for that, or maybe not, because I forgot to write it down here, but that will be in the notes. Yeah, good. Okay, so are there any questions on these things? Okay, so then, since we're up on...
I have a question about the, well, both, I guess. So here you're taking these basically soft graviton theorems, and you're writing them in this nice parametrization, and they look like 2D. So, but the operators that you introduced make a connection to the gravity side because you have the news. Couldn't you have just taken the Weinberg-Soft theorem and manipulated something on the left-hand side and gotten this?
That's what I did, right?
That's what you did?
Yeah.
Oh, sorry. So this...
Sorry, so this was the, so this, okay, so this is what we want, right? So we know the right-hand side is given by...
For me, n is a space-time quantity. So you're saying you have a full theoretical understanding.
But okay, so in the lecture before, and maybe we should talk about that again. So we had the, what was a graviton operator, h mu nu, space-time operator. We said, okay, let's see how we can define states at the null boundary. So then we took this graviton operator, I don't know if you can see, h mu nu of x, and we took the large R limit, right? Limit R large. Sorry? Yeah, because, or I just put in 1 over R here, and then we found that this was essentially given, so you do a mode expansion, so you have then an integral over omega and some coordinate w bar on the sphere.
The question was, did you have to refer to this gravitational notation at all in deriving this?
Well, here I have to tell you what that operator is, right? And that operator we got by, so, okay, you mean you don't want to start from the, you know, the commutator of the charge with the S matrix, you just want to start with the soft graviton theorem, with essentially this statement here.
I want to start with the Weinberg, it's just the field theoretical formula, where I guess what appears there is...
Yeah, actually that's what I did, right? Because I did not, we didn't have to write this. So the only thing that I wrote was this insertion of this, well, with the omega to 0 limit of the 0 frequency graviton. That was all I did. That's n. We didn't. This is not the charge, so we didn't integrate. We didn't integrate here, and we didn't use the. Well, we didn't. This is not there in what I wrote on the right-hand side.
So n is basically the Weinberg soft graviton.
Yeah. This is the insertion of a soft graviton, and that's what I wanted to say here. So we found what the n is by thinking about operators in the bulk, and then taking the large R limit. And we found that there is a saddle point. So there's so we write this in terms of modes, e to the I omega q dot x. You write this, we go to Bondi coordinates, so we replace x by u r z z bar. This is a function of w and w bar, it's a null vector. Then we found that if you write this in Bondi coordinates, that will be a piece that's proportional to r times an angle between this null vector is pointing to and where the space-time vector is pointing towards the celestial sphere on the night sky. Then we found that when you do the large R limit, there's this rapidly oscillating phase, which essentially gets localized by a delta function. That then told us that the spatial part of Q and the spatial part of X were aligned. In terms of the angle coordinates, the stereographic coordinates, that meant that the Z coordinate, which is in here, and the W coordinate, which is in here, become equal. And then we could, because there's a delta function, we could integrate. So there was an integral over omega and over WW bar. So this cell point localization allowed us to integrate over the angle coordinates, W and W bar, so that everything then, at the end of the day, depended only on the space-time Z and Z bar coordinates. And then we were left with the omega integral. And the omega integral, so that was then, that contained, because we do a mode expansion here, that contains the A's and the A daggers. And if you act with this on the vacuum, then one of the two will be 0, depending on whether it's the in or the out vacuum. And then essentially we arrived at this. And this is really, well, the insertion of a soft graviton at the, well, in the out state, right? We could also have, I've written here this element, but I could also have written the A plus in, but on the right here acting on the in state. So there we have a graviton on the in state.
Did you ever need to talk about
I did not have to talk about this.
Okay.
I just had to talk about this, which didn't refer to this story here.
Because in principle, I can write my n. I can write that n in terms of this A minus, which is the insertion of a soft gravity,
Yeah.
and never have to go through this Bondi, I don't know what, and right? Isn't this? I'm asking. Isn't this just a simple? Well, not a simple, but a manipulation of the Weinberg soft gravity?
Yeah. So the soft graviton theorem implies a water density for these objects that I defined here.
Okay, where n is just the insertion of the soft graviton, so okay, very good.
Because you also see there's no f's and y's appearing on the right-hand side.
Okay.
But now if you want to make the statement, yeah. If you want to make a statement that, yeah, okay, let's leave it at that. Yes?
But I think, so how I interpreted this, like this contact between the asymptotic symmetry group formalism and the Weinberg soft theorem, is that, okay, you can manipulate, as Monica says, the Weinberg soft theorem to give you this identity, but to interpret it as some charge commuting with the S matrix, you need the asymptotic symmetry group formalism. Else, you will get the same identity, but you won't know that it's a commutator of some charge of the asymptotic symmetry group. So I think,
yes.
is that okay? I also have another question.
That's, sorry, that's why, okay, I called it supertranslation current, so that's referring to, yeah, the fact that we are talking here about, and the stress tensor would be the enhancement of BMS to, I believe it's called extended BMS, where you have now the full local conformal group. Another question?
Yeah, I also have another question. So when you derive the Kac-Moody current and the stress tensor, so it seems like the Kac-Moody current comes since it comes from the leading subgraviton theorem, and we saw that the leading one is related to super translations, and the second one is the subleading and is related to super rotations, and so they seem to me like they are separate. So what I'm getting at is since they are separate and they come from two different symmetries, I'm thinking I can conclude that the stress tensor is not the Sugawara stress tensor mate of the Kac-Moody current, right?
Yeah.
Okay. So you have double conformal symmetry because you have one Virasoro stress tensor, and then you could make a second stress tensor with the Kac-Moody current, no?
Let me think. So there was, when people looked into the U1 Kac-Moody coming from spin 1 currents. They wrote down a stress tensor for that using the Zubgavara construction. Not sure. No, actually, okay, let me think. There was some work by Taylor, Stieberger, where they tried to make contact again after introducing this stress tensor. No, actually, sorry. You can write this stress tensor as sort of the double copy of this super translation current. Yeah.
Okay.
Maybe I'll talk about that when we talk about OPEs. I can add that.
Double copy in the amplitude?
Yeah, double copy in the sense that you take PZ and PZ with some suitable ordering prescription. Yeah. Yeah.
You square it, or?
Yeah, you square it, but you know, there's some ordering,
Right.
some normal ordering.
That sounds like Sugawa.
Yeah. I'm just trying to remember whether there was an additional subtlety, but I do not recall this now. But yeah, there was recent work, I think last year, relating the stress tensor to the Kac-Moody current. Yeah.
I keep asking you about the central charge.
Mm-hmm.
It seems related to this discussion because if the stress tensor is pure Sugawara,
then there's a central charge. Yeah.
Mm-hmm. The current bilinear.
Yes, and that was also in the paper that I was just thinking of. They, wrote down what the central charge would be. What I will say is that if you, and hopefully we're gonna get to that, when you compute the OPE of with the stress tensor, so that would amount to taking a collinear limit of amplitudes where you insert a graviton that has the same weights as the stress tensor, then you will find that the 1 over z to the 4 piece is 0. It's not there. And that's the statement that I made. Now, we do expect there to be a central charge at the end of the day, because what we know is that here also there is no 1 over z squared piece, so there's no level. But then you can actually get a level, but that will have to do with infrared divergences and dressings, and we're probably going to get to that at the end of the course. There is a computation that tells us what the level would be. It's essentially given by the gravitational Caspar anomalous dimension. But the computation of that involves some techniques which I'm not sure has been extended to the subleading case.
What is the gravitational Caspar anomalous dimension?
Well, we'll get to it when we get to it. But it's essentially, yeah, let's not get ahead of ourselves, otherwise I'll not get there because I have to introduce a few things in the meantime so that things make sense. Yeah. Okay, so I don't know, shall we break here and then talk about how to get to this two-dimensional story after break? can turn off the sound so that. Can you turn off the sound? I can hear myself. Okay, so let's look at the subgroup of the Lorenz group, which is the proper orthochronous Lorenz group, given by SO plus 3,1, which is the set of all 4x4 matrices with determinant plus 1 and the lambda 0, 0 component bigger or equal than 1. So this preserves the orientation of space and the orientation of the arrow of time, and we get back to the full Lorenz group by adding parity and time reversal. Okay, so we're going to look at this subgroup of the Lorenz group because there is an isomorphism, which is very important for our story, which is that SL plus 3,1 is isomorphic to SL2Z mod Z2. So here we're talking about 4D Lorenz, and there we will be talking about the 2D global conformal group. And I will denote the matrix, the 4x4 matrix by lambda, and the complex 2x2 matrix by M. And then let me maybe write here what SL2Z is. So I kind of already said it. So that's the group of all complex 2x2 matrices with the condition that it's a matrix that depends on 4 complex parameters, A, B, C, D, and the determinant should be 1. So that's what I've written here. Okay. Let's see, this is something like A, B, C, D. Okay. So now let me just try to motivate this isomorphism. And a convenient way to do so is to use the Infeld van der Waals symbols of the Lorenz group, which map 4 vectors to 2x2 matrices. So I have a 4-vector V mu, and I can make a 2x2 matrix out of it by using these symbols. Which are given by the polymatrices. So here we have the identity, and then the sigma i's, which are just the polymatrices. And then there is also a map that takes us back. And then what we can see is that we can write the space-time vector x now as a 2x2 matrix. So we'll have an x AB dot, which if you work this out with the plugging in the polymatrices, you get something like this. Let me just be very explicit here. So these are the Cartesian coordinates, x mu. Okay. And now you can work out that if you take this 2x2 matrix, ABCD, and you take this 2x2 matrix for the space-time vector, which is essentially this expression, then you will find that this transforms under SL2C under these 2x2 matrices. You can rewrite this as a Lorenz transformation under X news. Okay? And this lambda here will be given by a 4x4 matrix that now is given in terms of ABCDs. So this is some horrendous expression, which writing down doesn't really make too much sense, but let me just write down one component of it. Okay. From this, we see that the condition that we had here, lambda 0, 0 is bigger than 1. Okay. And then you can also show that the determinant of this matrix is equal to 1. And if you want to see what it looks like, I recommend you looking at this reference here, 1508-00920 by Lagos-Oblak. who is a postdoc at IPhT currently, who wrote a very nice set of lecture notes about how Lorenz transformations and the celestial sphere work together. And you will find the full matrix in there. And then what you can also show that there is an invariance under the reflection of m goes to minus m. And that is essentially the C2 quotient. OK. So now let's talk about the plane and how Lorenz transformations act on the plane. So we have a map from the complex to the complex, which is given by some function of the coordinates z, z bar on the plane. Let's just look what the options are. So we can have a translation, or we have a rotation, or we have boosts. Yeah, boosted relations. OK. Now we want to go to the sphere. And at the sphere, essentially, we have the complex plane, but we also have the point at infinity. So that's the Riemann sphere. So that z equals infinity is the point on the sphere, which I believe was theta equals to pi in the. So I'm using again the stereographic coordinates here. And now, because we're at this point at infinity, this map does no longer have to be analytic. So now this is given by az plus b, bz plus d, with ad minus bz being 1, which now is orientation preserving conformal transformations. And now, in addition to what I've written up here, we also have the following transformation, which are special conformal. OK, so far so good. And now let's have a look at how how Lorenz transformations act on the two-dimensional sphere. And what we want to see is that outcomes the global conformal transformations. So if I do a Lorenz transformation on my vector x, I'm computing this expression with this horrendous matrix here. And I would like to do this in the Bondi coordinates that we introduced before, so that we get a feeling of what happens there. So let me just remind you of what they look like. So we have, well, let me just write this out. Z plus Z bar. And we have I Z bar minus Z. And the last component is our 1 minus Z bar. OK? So these are just the transformation from Cartesian to retarded Bondi coordinates. And so now if you plug in this matrix and we go to Bondi coordinates, we can infer what the transformation of the retarded Bondi coordinates are. And what you'll find is that this is given by, so the radial coordinate goes to the radial coordinates times an angle-dependent function. So that's good, which means, because it means that the limit where you take r to infinity, which is when we go to future and past non-infinity, only picks up an angle-dependent function. Then u transforms with the same function, but its inverse. OK, there can be an order 1 piece, and here there can be an order 1 of r piece. And this function here is given by az plus b squared plus zz plus d squared divided by 1 plus zz bar. OK? And now the more interesting thing, and sorry for splitting this off like this, but OK. So now how do the angles transform? So here the z-coordinate can be written in terms of x1 plus I x2 divided by the radial coordinate plus x3. Now we plug in what this means, let's say to leading order. Let me just do this very explicitly. So here we already know what the transformation for the radial coordinate is. Okay, and plus 4 of 1 over r. And then what we'll find by plugging in this matrix over there, that this is just given by az plus b over zz plus d plus 1 over r. So what this tells us is that the four-dimensional Lorenz group, given by the action of lambda, acts on the celestial sphere at null infinity as the two-dimensional global conformal group. Okay? I guess this was fairly straightforward, or are there any questions? Okay, so now we want to arrive at this map that takes us from 4D to 2D. But before that, let me make a few comments about momentum space statements versus position space statements. And let me start with the massless case. Okay, so in the massless case, we have this null vector k mu, plus or minus for outgoing or incoming. And then we have this null vector that depends only on the angles, and we have that k square is 0, so this is null. And so this defines a cone of null momentum. And now if we want to embed the complex plane, and maybe I should actually do this here, complex WW plane into the light cone of Minkowski space, we pick the following embedding. Which, if you remember or look at the notes, we have already used before. The only difference is that now I have flattened the coordinates. So before we had also a 1 over w plus w bar everywhere. And now what this tells me, so I have this cone of null momentum, and now I can make a connection to the position space statement. So that was about the momentum space. My massless particles enter and exit at antipodal points on the celestial sphere at past and future null infinity. And via this parameterization of Q, there's a neat embedding into the light cone. So then we can, from the saddle point approximation, which aligns the direction towards which we point on a celestial sphere with the momentum of the particle, there's a nice labeling of massless particles by just their energy and the point on the celestial sphere at which they land. And I think I already did this before the break. We talked about the saddle point approximation of a metric perturbation, and in general you can do this for any kind of spin field, which localizes this, the direction towards which you point on a night sky and the momentum of the particle. And so there's a nice way of defining on square plus or square minus states. So let's say in the out state, I have a particle with momentum k, and let's say a spin plus 2. And this can then be obtained by the r to infinity limit of 1 over r, the integral over du. So this is a Fourier integral along u that picks up a definite energy mode coming from, so you do the saddle point approximation of this bulk field operator, and then you do this Fourier transform, and then you pick out the definite energy mode. Okay, very nice. Then let me briefly also mention massive particles, which we haven't really talked too much about. There we have a momentum p mu plus minus m, let me call it p hat mu. P square is minus m square, and this defines for me, or labels a point on the hyperboloid, which is parameterized by these 3 coordinates. So essentially, what we're doing here is we're looking at, the question is, how do we resolve when particles come in from past null infinity and then go out to future null infinity? In the first lecture, we learned that we can resolve these points with a hyperbolic slicing of Minkowski space. So those are hyperbolic slices, which is Euclidean ADS3. And then we can embed the hyperbolic space H3 into the unit hyperboloid of R1, 3 by picking following parameterization. Okay. Good. So I said that. And there's a similar cell point statement that one can make where for massive particles, which have a late time momentum, p square equals minus m square, and then they are characterized by a point on an asymptotic hyperbolic slice. And the statement of the cell point approximation then is that these particles, the trajectory is asymptote to ones where the spatial momentum is proportional to x. So, and here we had the statement that q hat becomes aligned with x hat. Okay, so that's what I wanted to say here. And now we can talk about the map from 4D to 2D. Okay, so let me do this for the 2 cases in parallel. So let me do here a massless case. Let me write again these equations. K squared equals 0 and K0 bigger than 0. And then let me do the massive case over here. Okay. Now, the first thing that I want to mention is something about Lorenz transformations, which is that Lorenz transformations act in a not so simple way in these z coordinates, but they do in terms of these embedding vectors p and q. So if you do a Lorenz transformation in these coordinates on the sphere, but now look at how this works for the null vector q, what you will get is the following: cw plus d to the minus 2, lambda mu nu q mu. And here, something similarly simple. So we transform these coordinates on the hyperboloid y, z, and z bar. And this is just a Lorenz transformation on this p mu. I think I'll put this one here. OK, and now what is the map that is supposed to take us from 4-dimensional amplitudes to 2-dimensional correlators? Let me just start to write that down. Let me call it the holographic map. So here in the massless case, we just label the point. We label particles by scale, the energy, and then a point on a celestial sphere. And because massless particles enter and exit at non-infinity at a point on a celestial sphere, this is a very natural. So we have a very natural location already on the boundary. And so the only coordinate that's sort of in the way of this two-dimensional picture is the energy, and that's what we will transform. So the map will be given by an integral transform in the energy, which introduces this, for now, parameter delta. While for the massive case, now we're not reaching null infinity. We are sitting here on some hyperboloid. So the map should include a smearing over all of these coordinates, y, z, and z bar. And the smearing is done via a bulk-to-boundary propagator, and that should be reminiscent from IPhT. And so we're using here the fact that we have this Euclidean ADS3 slices. And this bulk-to-boundary propagator will depend on these hyperboloid coordinates y, z, and z bar, and a point on the boundary. And to be explicit, this is just given by the following expression. And if we're now using this null vector q here, which is parameterized as such, then we can also write this as 1 over p hat dot q to the power delta. So that's the bulk-to-boundary propagator. OK. Good. So now let's plug in some on-shell states and see how they transform. So let's just start with scalar. We look at a plane wave, which satisfies box phi equals 0. And via this map, which is called a Mellin transform. This becomes some object that now no longer depends on omega, but depends on delta. And the plus minus for outgoing or incoming will turn into a label on the new wave function. So this will depend on the bulk point x, and it will also depend on the boundary point, w bar, and that will now carry the label delta. If you do this integral transform, what you will find that this is given by some numbers, some functions of delta. So there's a gamma function here. And then we have minus q dot x to the power delta. And this x carries a plus minus label because the Mellin transform, when you plug this in here, is only convergent if you regularize this. And so this plus minus here will be a regulator of the wave function, which I think I have not written down here. But it's essentially x mu plus minus I epsilon of the vector minus 1, 0, 0, 0. And if you go to boundary coordinates, what this amounts to is that you shift u to u plus minus I epsilon. So you go a little bit away from, so u equals 0 would be the light cone, so you go a little bit away of the light cone or of any other constant u coordinate. OK, so this is the expression for a wave function that is now supposed to be living in some object of definite. We want some objects of definite conformal dimension, and this is what we're going to see. Now let me also give you the map here. So we have some massive waves here, and they also go to some phi delta plus minus x mu plus minus w bar, but that's different. And what you will find here is that you get a more nasty expression. Can you still see here? Maybe not.
Yeah.
So these are given by modified Bessel functions of the second kind. So these are for massive scalars. And we can take the limit of this massive expression and recover the masses expression essentially by relating the ratio of m over y to the frequency omega. OK. So maybe let me erase here. Are there any questions so far? Okay, so now the objects that we have obtained, they will transform now properly under the two-dimensional global conformal group. So let me make this what the statement is. So let me make a definition here. And the definition is what is called a conformal primary wave function. This is an object, that we call it capital Phi, that carries a bunch of labels. So let me write down what the definition is and then explain the elements in here. So we define an object that has, well, the object is defined by the way it transforms. Okay, so we have these wave functions, which depend on a bulk point, x, and on a boundary point, w bar. They carry labels s, which is the four-dimensional spin of the particle. And then they also carry these labels delta and j. This guy here is the 3+1 dimensional spin S representation of the Lorenz group. So here I can have scalars, I can have vectors, tensors, I can also have spinors here. And then that will be the appropriate transformation matrix for whatever the indices are here. If I do a Lorenz transformation on the bulk point on which this object depends, and a Möbius transformation, so that's the two-dimensional global conformal transformation, then this object is supposed to transform in this way, which means that it's a conformal primary in the w bar coordinates, and it transforms as a four-dimensional, it transforms under the four-dimensional Lorenz group as objects with the appropriate spin should. Okay, and here again, we have this restriction that AD minus BC is 1. And the same for the...
Sorry, Andrea, as usual, I'm behind. So what you represented on the board, I can't see very well.
Oh.
So e to the ikx, it's supposed to be the wave function, which depends on x, which has fixed momentum quantum numbers.
Mm-hmm.
So I have the momentum labels, I don't know how many of them, 3 or something.
I have w bar and the omega.
But initially, e to the ikx, the key are momentum labels, because these are eigenvectors of the momentum operator, and the x is just the space-time dependence of the eigenfunctions, what you want to call them. And then you transform this to something that has one label and depends on, so which one?
No, so because of the way that the null particles hit the celestial sphere at null infinity, the w bar comes up for the right. And this integral here just replaces energies by deltas. So omegas by deltas. So here, this object depends on x, on omega. So this is like, depends on omega, on w bar. This depends on u, r, z, z bar, or, well, the Cartesian axis. This object still depends on all the x's, still depends on the bulk point. But now we integrated over omega, kept w bar for the right, and the omega dependence now turns into this label delta.
I see. So you've promoted two of the things that I used to call labels before into coordinates, sort of. Or
If you wish, yeah. Mm-hmm.
Okay, and now you're going to tell me that, so let's
for massless particles, I can do that, right? I can, the four null momentum of a massless particle,
yeah,
I can.
I agree. I was just confused about the notation more than anything.
Okay.
So now if I do it for a for a scalar particle.
Yes.
So massless scalar, then.
So here, I've computed for you here what this transform does for the massless scalar, and it gives you this function that's 1 over the null vector dotted into the spacetime vector to some power, and then with some function of delta, which will not be so important. Now I'm motivated. Okay. Well, I told you this is the map. Then I told you what the map does for the scalar case, and now I'm telling you more generally. First of all, what the transformation properties of this new object are, and then also allow for other spins not just the 0 case. So this was just, okay, so here I just dropped on you the map that replaces, so before when we had the stress tensor word identity, we saw that we should replace omega d omega by, we should go to a different basis, so we should go from omega to something else. So that's what that is doing. Then I've written down for you what that does, but I haven't told you anything about the properties yet. And similarly for the massive case, where this is much more complicated, we have 3 integrals instead of just 1, because we are not hitting the point on the sphere. At null infinity, we're hitting some point on the hyperboloid. Now, what I'm telling you is I'm giving you a definition of the objects that I want to consider in the theory, of which the spin for this spin s equals 0 case will be the one that's on the board over there. So here I'm just giving you the definition. This should hold for any spin. I want this object, capital phi. The s is there because it will have indices depending on what spin you have. And then the delta will be there because I already know that I want to land on something with definite delta. And then I will also have a 2D spin j. So the conformal group has these labels. So this motivates the definition, which is of a conformal primary wave function, that it transforms as something that is a 2D conformal primary, but it also depends on the bulk point. And because of that, it will transform on the Lorenz transformations. Now, there will be 2 types that we all will consider. Let me call them radiative conformal primary wave functions, where which satisfy the linearized equations of motion of massless particles. So, for example, the one that I've written down over there for spin s. So for spin s massless particles. And then we'll also consider what are called generalized conformal primary wave functions. Okay, satisfy linearized massless equations of motion for spin s. And here we will allow ourselves also to consider sources or non-analytic wave functions, for example, distributions. But this will be, considering these will be important for studying the conformal multiplied structure, and there's also some interesting space-time metrics which one can understand as generalized conformal primaries.
Okay.
Yes?
I can ask this now because I'm afraid we're going to really get into details. So first, over there, for the massive case, that transform is, how am I supposed to think about it? I mean, it's not the same transform that one does in the massive case.
Yeah. Because you're not, you don't hit, so you need also to smear to get to, so that's where the point WW bar comes in. There is no, so here we had this nice story that you hit the point and we had a cellar point approximation and everything was nice and you only are left with this one label that you have to exchange for something else. Here there is no nice way of interpreting, of relating this vector p to the point on the celestial sphere. So that's why we're doing this smearing. And while in hindsight, this is what you have to do such that the objects that you obtain transform as conformal primaries and solve now the massive Klein-Gordon equation in this case. So in hindsight, this is justified because it satisfies the properties of the object that you want to get. The limit is a bit tricky, and actually there are 2 terms that show up in the limit, and I think the shadow shows up as well. So, but you can take the limit and you can recover the massless case if you're careful and look at the convergent piece of the, for the rest of the course, we'll probably not talk so much about massive wave functions anymore. And also, it's not that developed. So the 2D side of things with massive particles is far less developed than the massless one. So I don't have too much to say there. OK, good. So also, I should say radiative, we also have that the 2D spin j will be identified with the helicity. So that's plus or minus s, while here, for the generalized case, we'll find that there's also wave functions that are primaries whose 2D spin is smaller or equal than s. Well, the magnitude of that. OK, so these will be the 2 types of wave functions that we'll consider. And now let me construct for you two-dimensional operators starting from that. Okay. So let me call this a 2D celestial operator. Okay, so this will be, it will carry also the labels of the spin, it will carry labels delta and j, but now it will only depend on a boundary point, w and w bar. And I should have said here that this also depends on the label plus minus, which is the label that we have in and out, that distinguishes between in and out states. Yeah, let me say a bit more in a second, but let me just write down for you the definition of a two-dimensional celestial CFD operator. It's given by an inner product of a bulk operator of spin S with the conformal primary wave functions. And here there's a complex conjugation, there's a minus sign. And this integral is taken over some Cauchy slice sigma. The plus minus again, the ones that shows up here, well, it's inside here. Maybe I just put that there, and then I can erase it here. So the operator carries this plus minus label, which goes to say that we are considering only one celestial sphere, not two, one at the past and one at the future. There's one that has some regions where operators are with the label plus, which would then correspond to them being inserted on scry plus, or there's operators inserted at scry minus, which would then come with the minus label. So here we have a single celestial sphere, and not two. Okay. What is going on in this expression here? So this is a bulk operator. So for example, a spin 2 operator, I would write this as, well, operator for spin 2 metric perturbation, which I would expand as we did before. So that would be d3k over 2 pi cubed, 1 over 2k0. So that's the Lorenz invariant measure. And then we'd have the sum over all the polarizations, plus and minus, of some polarization tensor epsilon mu nu with some polarization alpha. Then we have an annihilation operator that depends on the energy z and z bar. And I have e to the I omega q dot x. And then I also have the piece with the creation operator. OK? So that would be this operator which depends on a bulk point expanded into energy eigenstates. So this is what goes in here. And then in there goes the conformal primary wave function that I've defined for you on the board. Yes?
It would be useful for you to give an ADS analog of what you're doing. So am I understanding correctly, your conformal primary wave function is some sort of bulk boundary?
Yes, it is.
Like just to give a bit of a physical picture, because it feels like you're introducing a lot of...
Well, maybe can I write one more line to finish this story, and then we can talk about...
Like, just to make it clear why this is producing for you the operator that you want.
Well, that's what I'm gonna... OK, let me... First, I need to explain what the things are that I've written down, and I'm gonna tell you why this is what you should want. So here I've said there's an inner product of some bulk operator O hat, and then with the conformal primary wave function, now I have to tell you what this inner product is. So this inner product is an integral over a Cauchy slice, so that means we integrate out x. So that means that on the left-hand side, the object will only depend on w and w bar. The conformal transformation property, namely that this is an operator that's local on the sphere on w and w bar, and transforms with conformal dimension delta and spin j, is guaranteed by the conformal transformation properties of this conformal primary wave function. So because this transforms under the Möbius transformation and the four-dimensional Lorenz transformation as a conformal primary with dimension delta and j, so will the operator here. I've integrated out x, so this depends only on the boundary. And then this plus-minus label was inherited from the conformal primary wave function. and it tells me that there's a single celestial sphere, and I label the operators depending on whether I want to create in-state or out-state by this label plus or minus. And now let me just tell you what this inner product is. So let me tell you what an inner product for two spin 2 complex wave functions h and h prime is, so that you get a bit of a feeling of what is going on here. So this is given by an integral. Let me just do a constant time slice. So I have the 3xi. And then I have an expression like this. So this is essentially a spin 2 version of the Klein-Gordon norm. Okay? So I could have written down phi, d0 phi star. That would be the scalar case. And I could have written this whole thing down for a scalar primary wave function. But since we've done a lot of gravity and this has more structure, I'm writing down the same thing for gravity. And so there, if we want to consider wave functions h and h prime, which are traceless, this is all I have. And then also h and h prime exchanged. And so this is the, you can find this in Ashtegard, Cherenkov-Witten-Lee, Wald-Zuppers. You will see expressions like this. There they talk about symplectic products, but those are related to the inner product that I've written down here by removing the star here and adding an extra factor of I. So this is where this comes from. So now I've given you a definition of an inner product that I want to use. It integrates for me over the space-time coordinate. And the conformal transformation properties are determined by these wave functions. And so this will be now an operator, a two-dimensional operator that transforms as a primary with dimension delta and j. And it has the label plus or minus for in and out. OK, so that's the definition. Now, since Monica mentioned bulk-to-boundary propagator, so as you can see here, so we talked about this bulk-to-boundary propagator for the hyperbolic slices, which was 1 over p hat dot q. If you replace p hat by x, you get this object, which is also a kind of bulk-to-boundary propagator. But I'm not sure what you want me to explain what I'm doing here via going to the route of ADS-CFT. But I mean, yeah, I'm not sure what other picture I should draw for you.
Like if you were to do the same in ADS-CFT, what would you do?
But I'm not in ADS-CFT. I have a null boundary, first of all.
Yeah, but I mean, so in ADS-CFT, you'd be defining first the bulk-to-boundary propagator and then integrating it over bulk fields.
And this is what I did for the massive case over there. But for the massless case, this is not what we need, because we already have the point on the boundary, and then we have the energy label, which we transform.
Okay, so you need to do
I have to do one integral. Mm-hmm. And the example that I've given over there.
But just understand. So in ADS-CFT language, what you're doing is it this? You argue from symmetry arguments what the bulk-to-boundary propagator is, and it has to transform nicely. And then you simply integrate an operator into this bulk-to-boundary propagator to get the boundary operator. Is this what you're doing?
I explained what I'm doing, right? So I'm computing an integral over a space like slice, which I may want to push to future null infinity, of objects that transform under the global conformal group with definite weights. I've integrated out x, which means that the object will only depend on the boundary points, and it will have definite transformation properties, so definite weights h bar. This is the thing that we were after. We wanted to have operators. So we wanted to replace the S matrix, and this is what I don't know if I have still time. We wanted to replace the S matrix by a correlation function of operators with definite weights, and this is a way to do it. This is an approach that is a constructive approach that still links the fact that we started from a 4D picture, because these wave functions here are still 4-dimensional objects.
Thinking of this earlier, Monica, but I'm actually a little confused with O hat. So what operator do you choose for that?
I gave it to you, right? So here, okay, so here I've given you just a free mode expansion for a spin 2 operator. So if I imagine I'm a massless field that freely propagates, and I can describe it by, well, I have this free mode expansion. And then, yeah.
Well, I just mean phi is the thing which is anchored on the boundary, and we're integrating the bulk point against something via this inner product to get a function of the boundary coordinates, which is the object that you're constructing.
Yeah.
How do I pick O hat? I mean, is it just fixed by, is there any choice there?
So here, okay. No, I mean, this is the free mode expansion for a spin 2 operator. I can write this down for any spin.
Right, so that's what we always use. You pick the spin S of
I can expand it differently, right? I can, instead of expanding this in this creation annihilation operators in this energy eigenbasis, I could expand this into a basis where the A's and A's daggers have definite deltas. I can do that too.
I guess what I'm trying to say is, in Monica's analogy, where
I think it's
in
the
S side you'd be
shadow. It's the bulk to boundary of the shadow bulk operator. I think that's what it should be, and then you give the delta function when you integrate it against the alpha. Maybe that's what it is.
No.
Right. Yeah. So what I want to say, so maybe this conformal object that you've written the phi, maybe it can represent
Okay.
as a two-point function.
So, yeah, okay, good. So if let's say there is some subtleties there, which is why I didn't want to do it that way. But I could expand this into modes with definite delta and phi. So then I would have in the mode expansion, instead of these wave functions, epsilon times e to the I omega q dot x, I would have phis, right? So I would have, instead of the a's of a of omega, I would have a delta. So if I can, instead of this mode expansion, I can do the Mellin transform of it, right? I can transform this A alpha of omega to A delta with some alpha label, okay? And I could, so then these wave functions here will become phis, phi delta j's. And I could write this whole mode expansion integrating over delta w bar.
Why are you all still the A delta?
Sorry?
Why aren't your operators just the A delta? You're saying you already know how to do this on the boundary.
Sorry, what? What's the question?
So sorry, here you're writing the bulk field
Mm-hmm.
as some expansion in terms of basically boundary data. Is A alpha or boundary data or not?
Yeah, but this is the free mode expansion, right? So here I integrate, so this K, I integrate over, well, I can call it something, angles and an energy, for example, in the way that I've written before.
You change basis to delta and whatever?
Yes, and then I have the phis, and then there will be an inner product, there will be a delta function kind of contribution that picks out what kind of phi in the expansion will give me some number on, some operator on the left. So there will be operators here, and then there will be wave functions coming from this guy, which are now also conformal primaries, and then I can compute the inner product of one wave function and the other, which will give me a delta function, everything else will give me 0, and then I'm left with this operator and whatever else is
So
remaining.
the deltas are the operators that you're looking for.
Yeah.
But do you have a simpler, I mean, that would, I don't know, to me that would be a simpler way to introduce them.
No, because there are some subtleties in expanding this in a conformal primary basis. So this is why here I've written it in expanding it into an energy basis. There is, well, I guess I don't have time to discuss this today, but so okay, let me say this. So you can get a complete delta function renormalizable basis for plane waves for omega greater or equal than 0. So you compute essentially the inner product, which is the same inner product as I've written here, for plus minus I omega q dot x and e to the plus minus I omega prime q prime dot x. So you can compute the inner product, which will be given like some numbers, 2's and pi's, and then there will be so there's q and there's q prime, so let me say w and w prime, or let me write this in terms of maybe the k's. K and k prime, so 4-vector k and the k vector prime. And I have a 3-dimensional delta function here, k minus k prime, which this is proportional to. And I also have a factor of k0, and I have some pi's and 2's. Now, this was the plane wave basis. Now, if I want to study the statement of a complete basis of wave functions which now have definite delta instead of frequency omega, the statement is that this finite energy, positive energy plane waves translate into conformal primaries where delta is now constrained to be whose real part has to be 1 and the imaginary part has to be any real number. So the omega bigger equal than 0 wave functions in the plane wave basis, the fact that they form a complete basis translates into the statement that these wave functions here form a complete basis, but delta has to be restricted to this expression, which is also called the principal continuous series of the Lorenz group. And what I was referring to when I say that there's some subtlety is that when delta equals to 1, naively in this new basis, a mode is missing. And so when you write down the mode expansion in terms of phi deltas, you will find that there's only one mode that has delta equals to 1, but it's, so to say, symplectic partner mode is missing. And so that's why you have to be a bit careful in expanding this basis, for expanding these operators into this new basis. So that's all I want to say.
Just to make sure I understand, so for example, if I took just some massless scalar,
Yes?
I could just do this change of basis in a simple way. And then
As I did on the board. This is exactly what I did over there.
But
Yeah.
However, if I want to look at gravitons and soft things, then I have to be super careful, and then
No. So for the wave functions, you just do this, and it's quite easy.
Yeah, okay, I understand.
So let me say this. So these wave functions over there that I've written, this capital phi that had the label S, delta, J, and the plus minus, they are gauge equivalent to Mellin transforms of plane waves, e to the plus minus I omega q dot x, with some polarization vectors or tensors, or mu1 to mu n, plus minus. So if you take a plane wave, so this is the scalar, which just becomes this 1 over q dot x to the delta function. Now, if you address it with polarization vectors, you get spin 1 wave functions, spin 2 wave functions. You get also spinors, whatever you like. The statement, if you put in polarization vectors like the ones that we have used throughout this course, if you use polarization vectors that are not dependent on space-time, so they just depend on W bar, say, then this object that you get after Mellin transforming is only gauge equivalent to a conformal primary, but it does not actually transform as a conformal primary. And what you have to do instead is replace these polarization vectors, which, let me give an example. So spin 1 polarization vector, let me say the positive helicity, it would be given, I choose it to be given by the W derivative of Q mu, and then epsilon minus mu will be given by the W bar derivative of Q mu. And then I can build the polarization tensor from the product of these polarization vectors, and so on. Now, the statement is if I want to have a conformal primary of, say, spin 1 or spin 2, that's really a conformal primary, then I have to replace these by new polarization vectors, which are given by the old ones. But you have to shift them by some x-dependent term. And similarly, there's another vector, let me call it m bar, which is for the negative polarization. If you do this transformation, well, if you shift these polarization vectors by this space-time dependent factor, then what you get from Mellin transforming this expression now with the m's is indeed a conformal primary of spin 1 or spin 2 if you take the product of these. So this is the way to get any spin conformal primary wave functions. All of them have this factor 1 over minus q dot x to the delta. That's the scalar primary. And then you dress it with these polarization vectors. Or maybe I have time next time. We can also talk about massless fermions, and then you will dress it with, well, if it's spin 1/2, you will dress it with some spinner, and if it's spin 3/2, you will dress it with one of those and the spinner. And what's nice about these M's here, these space-time-dependent M's, is that they actually also transform with definite weights under the global conformal group, while those didn't. So the M here, for example, has delta equals to 0, and J equals +1. And you can see this just by doing a Lorenz transformation of this guy. And every W and W bar that shows up here in the epsilons and in the Q, you will do the Möbius transformation, and then you see that those are also transforming with definite weights. And so that's a nice feature. So then you can build conformal primary wave functions of any spin and conformal dimension delta just by Lego. You put together this spin 0 conformal primary wave function, which tells you what the weight is, and then you address them with these polarization vectors, which then tell you what the spin is.
So just coming back to your primary operators.
Mm-hmm.
So if I understand correctly, if I were just doing a massless scalar,
Mm-hmm.
I could just simply go from the momentum basis to the delta basis, and that would just give me the operator, right?
The massless wave function will give you the conformal primary wave function.
No, I don't want to do wave functions.
Yeah, but what do you start with then?
Can't I just go from the creation annihilation operators in the momentum basis and just transform them to the Mellin basis, and
Mm-hmm.
that would be it? For scalars, there's no issue. Is that correct?
Yeah, I mean,
Those would
essentially that's what you will pick out.
you just want to go to a basis which has nice transformation properties
Mm-hmm.
under.
Mm-hmm. Mm-hmm.
Okay.
And this formula gives me that for every spin.
And then, if I understand correctly, if you want to do particles with spin, then it's a bit more complicated because there's a lot of subtleties. So the best way to do it
Mm-hmm.
is to go through this conformal primary wave function. So I can't just naively transform the creation operators in the momentum basis because there are a lot of subtleties. So better I go through these well-defined conformal primary wave functions, which somehow act. Maybe I can represent as some sort of correlator of a shadow bulk operator and the primary operator on the boundary, roughly speaking, such that when I do this inner product, I just pick up a delta function and they just give me back the boundary.
Yeah, I don't want to quite talk about the shadow one because there are a lot of subtleties which maybe we'll discuss next time. Essentially, for the particles with spin, the subtlety here is that there are zero modes, and those zero modes are you have to be careful not to miss zero modes when you do this directly from the, because when you have soft gravitons, for example, will then be operators where the conformal dimension is taken to certain values, but you don't know that beforehand. So you don't know what value of delta that would correspond to. Well, you can look at the Mellin transform and then figure that out. But a priori, this gives you a way to construct 2D operators with any delta, any j. This doesn't have to be on the principal series. It can be any delta in principle. And then when you ask questions about completeness, you land on the principal series. But then what we will do next time is ask questions about where the asymptotic symmetries come from in this two-dimensional story. And there we will find that delta cannot be on the principal series. And there are subtleties related to those zero modes. Yeah.
Just a couple questions.
Sure.
I mean, in Monica's picture of doing the scalar in this different way with the modes, I mean, when you say the word basis, you're using that delta is constrained to lie on that line. So something is...
Exactly. And the point is that actually the asymptotic symmetries will not lie on this. So, okay. You might ask the question, okay, if, so I do this mode expansion and I keep delta on the principal series, but then you find that there's all these modes that correspond to all the asymptotic symmetries that people have found, which do not lie here. So then maybe your first question is, do you have to add them? But that's not what you should do because you already had a complete basis, so yeah. But then you can find that you can actually obtain those modes by deforming your wave function on the principal series via some contour integral in the complex plane. And there was a way to do that. Although there's, a couple of questions and issues and subtleties evolving around that. Also about the question, what's the best way to represent the celestial data? It seems that if you want to talk about symmetries of the S-matrix in that new basis, which we'll call celestial amplitudes, then those become clear when you're not on the principal series, but you go to either integer, half integer, or maybe the real deltas. So these things will become clear here. Another thing, okay, now this is getting a bit disorganized, but let me just mention one thing since we talked about the supertranslation current. The supertranslation current in the new basis, P mu, can be represented as this null vector Q mu, and then a differential operator that's an exponential operator, d by d delta. And what that does when you have this operator, this supertranslation operator in the OPE with an operator of dimension delta, what it will do is it will take the dimension delta to delta plus 1. Now, if you take delta to delta plus 1 and you originally had an operator on the principal series, it will no longer be on a principal series. If you had an operator that had integer delta, it will be shifted, and it will shift further and further up as how much you act with the supertranslation operator. By the way, this is exactly what we talked at the beginning of the lecture, where we said, because in the water density for this supertranslation for this Kac-Moody current, there was a power of the energy. This power of the energy turned into this shift in delta. So what you see now here is that in this new basis, translation symmetry is no longer manifest, and it does this funny thing of shifting the deltas. So yeah, maybe this led to more confusion than explanation, but maybe the bottom line is that there are still things that are subtle, things that are not fully understood, and even the question of what's the best representation of the asymptotic data at null infinity is also not sorted out yet. It's also a question about shadows and light transforms and so on.
This question might be better suited for next. Tell me if so. But isn't there also a discrete component to the basis in 2 dimensions?
Yeah, there's, so when you take delta to be on the integers or on the half integers, this is what we will do, what we'll talk about next time.
But when you say that's the basis, it's almost the full basis, but it's not really.
By this, I mean that if you, so here to make the statement about completeness in the energy for plane waves, you show that the 2-point function, so that this inner product is a delta function. Now, if you Mellon transform, you put in the phi's in here, phi delta prime in here, you will find a delta function. So you'll find essentially the integral only to converge and then give a delta function if this is the case.
I see, but
that's the statement.
It doesn't necessarily a priori have to map exactly the basis of the wave functions for the 2D conformal group, which includes this discrete piece as well, does it?
And what does this correspond to in, so here, so that would correspond to 0, maybe I should do this. Well, not quite, maybe, okay. So delta equals 1 is already 1 0 mode, so that's why I kept the thing here. But then if you take deltas that are other integer values, you get other 0 modes. Yeah, that's maybe all I have to say.
Last question, I think this is simpler. Why does O also have an S label?
Ah, good. Because phi also has an S label.
But then we integrated against something which soaks it up, and the thing we're talking about is just living on the boundary, so there shouldn't be any more information.
Yes, but so here I distinguished what radiative and what generalized means. And apart from what equations of motions are not satisfied, here the 2D spin is fixed up to a sign to the 4D spin of the particle. Whether it's plus minus S or minus plus S depends on whether you have the wave function or the shadow. But never mind, the magnitudes are equal. While for generalized, we will find wave functions where the 2D spin and the 4D spin are not equal, not even up to the sign. So for example, we can find wave functions that have 4D spin 1, so they would correspond to, well, spin 1 objects, which can have a 2D spin 0. And we will see this when we talk about the descendancy structure, because descendants, so the L minus 1 and L bar minus 1 essentially correspond to derivative operators, and those derivative operators will shift the H and H bars. And so we can start, for example, from an operator that has j equals 0 and then descend to 1 with j equals 1. And we're going to talk a little bit about this next time. Let me give you an example maybe. So maybe that's a good note to end on. An example for generalized conformal primary metric. Okay, so let me write down okay, let me try to find the best expression for that. And that's the last thing that I'm going to write down because we are already over time. Okay, so let me consider let me consider a metric perturbation, which is given by one of those spin 2 wave functions, which because it has spin 2, it has two of those polarization vectors m. And then I call phi delta this 1 over q dot x piece without the gammas. So this is just minus q dot x to the delta. Okay, so this would be what I'll call h mu nu. Now you can show actually that, so this, you would say this is a spin 2 solution to the linearized, so this is a solution to the linearized Einstein equations, this object. I just constructed it from, well, a wave function that was, this is a solution. And it was constructed in that way. But now you can notice the following. You can notice that this vector mu is null and geodesic with respect to both eta and g. So it's null and geodesic with respect to both these metrics. What this then tells you, because of the way that I've written it here, is that k mu is a so-called Kerr-Schild vector. And if you can, so because it is a Kerr-Schild vector and because of these properties, this metric, what you think is a metric perturbation, will also satisfy the exact Einstein equations. So now this full object is an exact solution to Einstein's equations. And this goes to say that conformal primary metrics, h mu nu, which have delta and j equals plus minus 2, are solve Einstein's equations exactly. Okay, so that's the first thing. So these are these phi's with j equals plus or minus 2, and they are exact solutions. Now I can write down, so let me write down another solution here, which maybe some of you will recognize. So, or maybe, well, maybe not. So there's another exact solution to Einstein's equations, which is so if there's someone very GR in the audience, they might recognize it as the Eichelberg-Sechsel shockwave metric. So this guy here, which also looks like a perturbation, is actually also an exact solution to Einstein's equations, and it's the Eichelberg-Sechsel metric. And the way that I've written here, this vector q here is a null vector, but this is also the null vector that we, so this is this null vector here. And so you see it has distributional support along q dot x equals 0, and then it also has this logarithmic piece, and it has energy given by this value alpha and q0. Okay, and what you can now see is that this object here is a generalized conformal primary metric, h mu nu, with delta minus 1 and j equals 0. Okay? So you can see this by, so I gave you way before the transformation properties of the q's. This is invariant under Lorenz because it's x squared, and then we have delta q dot x. you can do the Lorenz transformations and the Möbius transformations of this expression, and you will find that it looks like an object that has dimension -1 and 2D spin equals 0. And so that is an example where the 2D spin and so this is still for a metric, right? So it's S equals 2, but J is not the same. In this case, J equals 0. So this is an example. So that's one use of these generalized conformal primary metrics. You can describe solutions that we already know, and these are exact solutions to the Einstein equations. So it's kind of nice because we can say that the Eichelberg-Sechsel metric transforms as a generalized conformal primary. So hopefully we can do maybe some scattering on top of this background because it has conformal transformation properties already. Maybe we can do some scattering problem where everything has definite conformal transformation properties. So this is also the ultra-boosted black hole. So in a sense, we can also describe the ultra-boosted black hole in this celestial CFT language with definite delta and J.
So these O's are not fully specified by their 2D conformal data, delta and J. Correct?
In that sense, from here, you also have to give me the 40S. If you just focus on the sort of conservative thing, which would just be considered what we call radiative conformal primaries, then J is fixed by S, and then you get guys that satisfy the master spin S equations of motions.
But yeah, see, I mean, the reason I'm trying to do that, so to speak, is because if we're making a 2D CFT picture of what's going on, well, these operators O are not 2D conformal primaries. They depend on more data than that. So they're not just
yeah, and also the plus minus label.
A 2D CFT, right?
Also the plus minus label, yeah. Yeah.
So it's not, we should not call it a 2D conformal primary in the ordinary sense of the word.
Sure.
Thanks.
Okay, maybe we can. Sorry,
Did you want to say?
No, I just wanted to say that's tied to the fact that the plus minus you would have looked at the CFT on one sphere, right? And then you would just have the labels delta and J and the point. But now we want to do scattering between two spheres, but we want to consider it as the same sphere, where different regions on the sphere tell me about whether the states are in states or out states. So it's not, it already is, not like in ADS-CFT where you just have, on the time-like boundary, you just evolve along, but here you have the two spheres and you link them. Yeah. I mean, there's also this issue with the matching condition that we have to do on square minus and square plus, right? So the two spheres are not independent because of this matching condition, and now we say it's the same sphere, and we just label the in and out states by this plus minus.
So the inner product doesn't totally eliminate all of the S dependence. It's not as if you have two things whose indices are contracted and the remaining thing has no. I thought that is right, because those are both. We integrate over the x's and mu news, but then the operator can still have. So here I can plug in a phi which is a metric. Then I integrate over the x's, and I get some j. But I mean, the j doesn't have to equal the s here. So. You've got lots of different choices what to put in the inner product, but then once you perform the inner product, you get something where there's no S dependence in the sense of there being no floating indices.
Yeah.
But you can choose lots of different J's with respect to the S of the thing you plug in the inner product. But what pops out doesn't truly have S dependence per se. It's just
It doesn't have indices anymore.
To begin
Yeah.
with of how to construct these operators O for fixed J.
Mm-hmm.
Okay, so it's sort of more.
But I keep track of what the S keeps track of whether you had whether you had indices in the thing that you constructed it with. And yeah. I mean, in the same sense as we have this distinction here for the wave functions, we have the distinction here for the operators. if we look at descendancy relations for the operators, descendancy, like the derivatives, will change your J, but it can still come from the same. I mean, you start with some spin S wave function, and then you can get different kinds of deltas depending on what the descendancy structure here is. Yeah, so there are many things that are not like in CFD or that we know in alias CFD. There are various subtleties. Many come from the fact that we have this infinite enhancement of symmetries, which we'll talk about next time. I didn't get to, I'm out of time now, but next time I will write down celestial amplitudes that have these operators. You can think of them as correlation function of these operators. And they also have some funny features that are not as in vanilla 2D CFDs. So, yeah. I mean, I'm over time, so let me stop here.